Well, hi, thanks so much for joining me here in my shop. Today I'm going to be doing a lot of tube testing. In fact, the last week I've been doing a lot of tube testing in here. But as you can see, when you look at my bench, I've got a lot of commercial tube testers out here. 1, 2, 3, 4. This is the one that I've been restoring here. What's a little hard to see is what's going on right in the corner here. So let me switch cameras. I'll show you what's in the corner. So this is my own testing rig or jig, if you like, and I've been working on. I shot hours of video of me trying to make this thing work. What this is just a jig for a tube, and then I use my shop equipment to fire up the tube, adjust all the voltages on it, and then all these instruments to measure currents and voltages on the tube, ultimately so I can determine the GM, the mutual conductance of the tube myself, independent of all these commercial testers. Then the concept is, because I know for sure from what I did here, and believe me, it's just a concept. I'm not so sure I know anything for sure from what I did there. The next thing is test a tube in all these tube testers. Now, I'm going to do this with 6S and 7s. I have a lot of them. These are all 6S and 7s of unknown quality. I have more than that, in fact. So I plan to run them all through my tube testers here and ultimately understand the tubes I have and what quality they are, the tube testers I have, what quality they are, including this one. I don't know if I pointed this one out over here. This is just an emissions tester over here. And ultimately compare the GM readings that come out of this tester, and this tester against what I'm doing over here. The object of this was to get an objective, independent, and detailed, sort of hands-on measurement of the GM, which it seems to have worked. In fact, I seem to have been able to do it. So now it's time to take the tube I've measured here and measured in each one of these. Well, what I realized about these tube testers, one thing I didn't understand. Well, I'll start with the assumption. The assumption I had was that these tube testers basically mimic what a radio does to a tube. Sets up the same kind of B+, the same kind of bias, the same kind of everything. But I don't believe they work like that at all. Not at all. In fact, most of these guys don't even have filters to produce a smooth DC. I'm not sure how true that is, but often they are not applying simple DC voltages to the tube under test. They're applying some sloppy signal of a weird sort, and through their circuitry they're able to derive the GM or something very close to it. Close enough. In fact, I'm really suspicious that these machines are built to be flexible enough that no matter what tube is plugged in here, there is some setting of a vernier control, this bias control on this one, or meter sensitivity on this one, or grid bias on this one. These vernier controls, or smooth, non-snapping controls, are really in here so they can find a setting on it that results in the proper reading on the meter at the time they're building and marketing these machines. So yeah, they really do seem to measure GM, but they don't do it the same way I'm doing it over here. That's enough speeching. Let's get going. I think the first thing I'm going to do is test this example tube. This is a Jan. Oh, maybe this one isn't a Jan. So it doesn't say Jan Joint Army Navy on it. It looks like one though. It has the right color base and the light, but it doesn't actually say on it. It says CBS. So I'm going to test this tube through each of these tube testers. I'm going to have to practice on this one again and see how it compares, and then I'm going to stick it in my jig and I'm going to try to read it correctly, whatever the mutual conductance is. So I may as well let you watch me do this. So 6SN7 is a 2-part tube. I think this guy is already set up for him, because I tested him just a minute ago, or a day ago, yesterday in fact. 6.3 JX. I'm trying to hurry along here because I realize from experience just what the volume of work is ahead of me. It's a lot. 2373. It's a lot if I'm going to be doing this. Each one of these tubes is actually 2 tubes, so that's a lot of testing. We're good. In she goes. Now, I'm going to need some kind of recording system here to track all this. For now, I'm just going to scratch it on a piece of paper, and then I'll figure out a much better way, because the volume of tubes, the volume of tube tests that are coming, I don't plan to test every tube through all these tube testers. I just plan to do a number, like maybe 3, 4, 5, until I become certain about the operation of each one of these testers in comparison to the other. And the fact is, I've always had faith in this tube tester, and this one has proven itself. So this guy's new. Okay, I think we're ready here. Do the short test. Okay, I can't put that there, can I? Check the line voltage. Now I'm going to get confused between all these different tube testers. The line voltage is right on. So this tube is testing at exactly 2000. And as I say, this is just the first tube. I'll call it that. First tube, Stark, and one side and the other. One side gave 2000. Now the other. So this is the kind of thing I'm going to be going through here over and over. JX2103, 2103. Not all tube testers can you be turning these knobs while the tube is in place. 2103 with a 5. I thought I got something wrong there. 23 and 73, P4, shorts, P4, and this one tests right on 2000 also. So this is what these tubes are supposed to read. How do I know that? It says right here, 2000. 2000 is good, 1260 means throw it out. Where did they get the 2000 from here? Now that's a really good question, because if you look up the GM for 6SN7, we're going to do that right now, just to show you how the confusion starts right off the bat. Right off the bat. So there is no such thing as a GM of a tube. It's GM of a tube under its operating conditions. So this is a 6SN7. This is the RCA Bible book, one of many. And we look here and it says, well, the transconductance is 2600. 2600, but it says 2000 here. And it reads exactly 2000. See, to me that's really suspicious. That's really suspicious. My own testing jig, I've previously tested this tube at 1500, but you see, it's under the circumstances of the test. It depends on the grid bias setting. It depends on lots of factors control the GM. Not just the condition of the tube. So now we're going to go over to this guy over here and do the same test. So I think he's also set up 6SN7, 6.3 to 18H GPK53 GPK53 17601760 28 and F. Okay, so this is all set up. And this one, when you want to do the other half of the tube, it's just a matter of throwing these switches. Kind of similar to my own tester. I have a switch on my own tester. We'll plug this guy in. Good. Now, let's bring the camera around. See if we can't get that to show up here. There we are. It's very, very tricky to get these things to be able to read the dial scale because of camera issues. There we go. Okay, we're all set. I've already double checked it. So on this, it says 840 is the rejection point, and it also says times 2, which means you take the reading on the scale, multiply it by 2, and that gives you the actual GM. 840 is the reject point on this machine. On the other machine, the reject point is 1260. Now, what's going on with that? Couldn't tell you. Okay, let's make sure that we don't have any leaks. GM, line check. Okay, and GM test. So we're reading, I guess we're reading on this top scale here. 1,000, 1,500, so that's about 1,250 on here. Kind of shaking around. Don't know why it would wander around like that. So that's a little higher now, about 13. 13 times 2 is 26. 26 is what's written in the book. Now, this tester doesn't give you a high number. It just gives you the low number, the rejection point. So you get anything above the rejection point, that's okay. So what's that tell you about this tester? So maybe this thing is designed carefully so that when the thing is reading a rejection point, it really should be rejected. But any reading above that doesn't really mean anything. It's not actually. Well, I think this claims to be a mutual conductance tube checker. Before inserting tube, set filament voltage, set leakage switch to 1. I never saw that before. Return leakage switch. Oh, position 1 is here. Tube test. Okay, no problem. That's half the tube. Here's the other half. Getting exactly the same reading. So they read the same, but they read differently. They read the same, both halves on each tester, but between the two testers they don't read the same. 2600 on that tester. Just writing it down here. Okay, now we're gonna switch over to this one. And I'm gonna stop the camera for a while I remind myself how to operate this machine. Okay, and I got to get the lineup, the switch settings for a 6SN7. Okay, so I think I'm ready to go with the precise tester here. Let's just review these settings to be absolutely sure so I don't make a mess of things. 6SN7 CGGG, CGGG, this one doesn't matter, in GM mode. 02014, 02014, and 25600, 25600. Good, all set. On test, switch off, and bias on the 10 scale, bias required for this tube according to the machine is 3.6, and now that's another interesting thing. This guy gives a bias voltage setting that you set on the meter. This is different from these other testers. So you actually have control over the bias voltage. At least you adjust this to make that meter read the number on the chart. Is it really 3.6 volts? I can't remember all the testing I did. I think it really is 3.6 volts. But that's an unusual bias for a 6SN7. A more typical bias would be -7, -8 volts, not -3. So what's this guy doing? He's not operating the tube the way I'm going to operate it over in my jig. Again, this thing's doing something different, and because I have a lot of information about this tester, I know it's not applying DC voltages to the tube as it's testing it. It's applying chopped up 60 cycle signals of some sort. It's a wild guy. He's wild. Let's give him a tube. Oh, let's give him a tube. Hot tube. There you go. Interestingly enough, this tube tester will allow me to read the filament current directly, which I found in my own experiments here is, I think, really important to really know for sure what the current is that's going through the heater. So you know for sure the heater is producing the right amount of heat in the tube. Without doing that, well, you're just going to rely on the end result. Maybe it's going to come back low. You'll never realize, of course, these tube testers don't tell you what's wrong with the tube. They just tell you that it's not up to snuff. And by the way, why measure GM anyway? Why not measure plate resistance? Why not track tube quality with plate resistance? As the tube wears out, the plate resistance goes up. Why not just track that? Because this is the whole deal with GM. GM is a combination of two factors which get weak with age. The two factors are multiplied together to give you the GM. The GM becomes a product of two factors that either one indicates weakness in the tube. If the two of them are weak, the GM is down and out. So the GM is important for other reasons too, but as a tube testing number, it tells you two factors, the condition of two factors in the tube, and I couldn't even tell you what they are. Emissivity would be one of them, I guess. I don't know. So that's why GM. That's why these things want to test GM, as opposed to this guy over here, which just tests how much current flows through the tube when you put voltages on it. That's a different kind of test. Now this guy will do both those tests. See, it says model GM and EM tube tester. This is the baby. Okay, I'm talking enough here. Let's get this guy going. I have it in my power supply. Just making sure we're good here. I think I need to plug it in before I go any further. There it is. Now I got so much equipment on my bench here, and you know, there's all kinds of there's metal cabinets here, two-prong plugs going in all over the place. So to me, my little, you're going to get a shock gem antenna is wiggling. So let's just take a look at that possibility right now with my high-tech tester here. I think with all these meters around, I'd use them. So it's lighting up there. That's not too good. Let's try it over here. That's lighting up here. Let's split. Now you know what? This shouldn't. Plugging it into an isolation transformer. It shouldn't. It shouldn't light up. Still lighting up the same. Not lighting up over here anymore. I'm going to reverse the plug on this guy. Cannot reverse the plug. Oh, okay. So I'm going to have to just keep in mind I best not be touching both of these machines at the same time. I'm not on my way to getting a big shock. I'm on my way to getting a little tickle. Just as soon not get it. Good. I think we're all safe and ready to go. So we're going to switch the power on here, but I'm going to switch the master power over here on my control panel. I've got dim lights in. Let me just move the camera up a touch. These lights will come on when this thing's warming up, unless something really seriously good. Something seriously has gone wrong. No. Let's give it a double bulb treatment here. Good, everything's fine. So I'm going to give it full voltage. Take the dim bulbs out of the circuit. Now, procedurally. Wow, can I remember all this? I think I can. Let's see. We'll take a peek at the line voltage first. It's a little high. Got the tube in. Bring this down. Okay, now bias was supposed to be 3.6. We're on the 10 scale, so I got the bias high according to this. So we'll take it down to 3.6. So, better read the right scale when I do this. 3 on the 10. Yeah, I'm reading the wrong scale. 10. So 3.6, much lower yet. 3.6. So that's 3.6. So it's set in accordance with the instructions for this tester. Go back and look at the line now because it will change the current flow in the tube. The line is fine for the kind of precision we can expect. Okay, bias. You know what I didn't do is I didn't do the short test, but you know this tube's been tested quite a few times for shorts, so I'm sure there isn't any shorts. So go into test mode. I flip this over to test and read the GM directly on scale C. Scale C is, well, I guess we just go 8K. So I look for the 8 scale. The expectation is only up around here. There we go. So it's right up around where my finger was. So this is reading a GM of 2000 dead on. Funny how that number keeps coming up. And now let me just quickly look at the instruction page and see what it must give a rejection point. 6SN7. You know what, they don't. Yes, they do. Oh, this says 1650. 1650. Now, oh man, is that the rejection point? It can't be. Not that high. 1650. 1650. Put this on hold. And I'm getting 2000. Well, I'll have to do a little research to see what the chart really means when it says 1650. Because again, this is all about, like these testers are creating their own tube testing environment. And the guys who designed this figured out what they were doing with respect to what they were doing. So what's going on in here is not what's going on in there, is not what's going on in the other tester either. Somehow they get to the same spot, and as I said before, I think it's all about fiddling with this control here. So literally, they have a tube, they know its GM is supposed to be 2000, that's how it should test. When they're developing this machine, they put the tube in, they set everything correctly, then they do this until they get 3.6. Not 3.6, but until they get the correct mutual conductance reading here. When they get it, they make a note, set the bias to whatever this should be. And what is it set to, Jim? Just under 3.6, because I was wiggling it. So I think that's where the 3.6 number comes from. Them forcing the machine to read the right thing when a good tube is in it. I don't know. I don't know if any of the guys who designed any of these things are still alive. Who knows? So far, all three of these testers are indicating this tube is good. We have one more tester to go through here. Let me just take a moment and get that one ready to go. Okay, hold on a minute here. We're not done with this guy yet. So this guy will read the current flow through the heater. And I know what it is. It's 0.6 amps. It should be. So let's see. So, oh my gosh, this is on bias. Okay, that shouldn't be like that. Shame on me, that's okay. Here we go. So on the 3 amp scale, because it's 0.6 amps, and there's a lot of stuff on this meter, way down at the bottom here. So we're reading just a little above 0.5 on this meter, close to 0.6. No way you could, well, I don't know. Maybe that is the current flowing through this tube, because the voltage that this tester is putting on that tube is whatever it is. For instance, if I move the this up and down, it's hard to see, but the meter is moving up and down, and that's going to change the temperature of the filament, and that's going to change the result of the test. How much, Jim? That's a sensitivity thing I've never ever studied. Let's try that. So go to test, go to test. Okay, so we're reading GM now at 2000. I'm going to move the, basically change the temperature of the heater. Look at that. It's, well, you know what, I'm changing a lot of other stuff here too, aren't I? I'm changing all kinds of stuff. That's kind of a false notion. Jim, that's a false test. False test. At least I can recognize a false test. At least I think I can recognize a false test. Okay, so we read the current. There's no other fancy tricks on this one, I don't think. The EM, yes, there is a fancy trick. We can go from reading GM to reading EM, which I've never done on this machine, I don't think. But it's all calibrated and ready to go, so let's try it. How do you do that? Okay, so first of all, I want to turn the machine right off, I think, while I set this up, because I'm not sure if I can change all these. Probably can change all those, but while the tube's in, let's not find out today. So BFBD. BFF. B, that must be an E. Yeah, EM test, B, and then D, and then this setting is set to 9. Okay, so this is the vernier that they use to cheat the result into what it has to be. That's my thinking on this stuff. Doesn't make it invalid. It just I think it's really good to kind of know what they're doing with these machines. Or if you think so, 02014, that's the same. And then, wait a minute. 02014, and then 25600. 25600. Yeah, so the variation here really is in this setup. This is kind of whatever the tube is, it's going to be, I think. And then this is the things you're varying between the GM and the EM. Jim says, teaching himself how to use his machine. So we're ready to go in the EM test now. So we'll go power on. Okay, I put the dim bulbs in again because I'm just a little worried about this guy. No need to worry. He has his own dim bulb right here. The fuse light is actually a dim bulb. And if you don't know what I'm talking about, type dim bulb safety or something like that into Google. Lots of guys will explain it to you. Okay, so we'll go through the proper procedure again. Check the line. Looks okay. Bias. I don't know if there's a bias setting in this mode. Wasn't there something special that had to be done? 6SN7. Bias is set to 16. So what's special about this now is instead of setting it via the meter, you set it via the actual numbers here. So 16 is right there. And I put a new potentiometer in there. Its linearity may be different. It is different. There's no doubt about it. So is 16 still 16? Probably not. But not much I can do about that. Put that into test mode. Here we go. I think this is the first time I've tested a tube using this method. And now it's all good and bad up here. It's just good, bad, indifferent in the middle. I think we're ready. Here we go. Oh, so pins my needle. I still have trouble with this meter sticking up here. So it's clearly shooting up into the good. We can't get a full reading on it. Okay, all indications are this tube is good, including the fact that it looks brand new. I mean, that's a pretty good test in itself. Let's go to the EM tester now. This tube, and I'm only testing one half of this tube sometimes because I'm trying to get through this. Okay, before we put the tube in, a 6 SN7, 26 on this dial, so this will be the gain, the vernier that is used to make the thing read right when they're figuring out all these numbers, I believe. There's another one, still 6.382. Just muttering along here while I do this. 1, 2 are up, 3 and 7 are down. That's the way it is. Power on. Lights came on in there. Let's put the tube in. Tube in. Just double check the voltage. 6.3. Tube is in. Short and merit. How does one control do those two things? So we'll check the line adjust. Bring it up. Set that to 2. We're ready. Good or bad? And of course it tests right in the middle of the good. And we can do the other side on this one easy enough by flipping. Should I get this right now? So 1 and 2. Oh my gosh. So 1 goes to the middle, 4 goes up. 3 goes to the middle. This is quite different. 6 goes down. So 4, 5. Oh man, let's start again here. I can see that it's better to re-zero them. 2. Right. That's what's so clumsy how they've done the numbers here. 4, 5 up, 6, 7 down. Oh, it's just warming up. So some of these are engaging the heater, obviously. I think these two would be the heaters, the ones you flip down. And there it is up in the good. No surprise at all. And now what I'm left with is my own test jig, where the truth shall come out. The truth about something, anyway. It's going to take me a little while to get that set up and ready to go. So that's what I'm going to do. Okay, so hidden in the corner here, all this wire and these meters, is my own personal shop tube tester. So we're going to do the same tube. And let's fire this guy up now. It's all a little bit nerve-wracking for me because I've shoved everything around here, but hopefully we don't have any problems with shorts or something like that. So we'll start with the DC power supply. That's going to fire up the heaters in here. So this is going to read the current flowing into the tube. Just a little too much for my supply to start up with a load on it. So you can see the inrush current was up over 2 amps anyway initially. And it should settle in at 0.600 or very close to that, simply because I've adjusted the voltage level of this to ensure that there's 0.6 amps flowing here, and of course that varies a little bit with the house line voltage, just a little bit. Okay, so what's happened now is the tube is warmed up, but it doesn't have any voltages on it. Let me just get this out of here. Okay, so the power supply I've been using It's right there behind the microphone. Right there. We're going to put them on standby. Turn down the B+. We'll start with no B+ voltage. The C- here is probably set to -8 right now. That voltage is reflected on this meter. Grid voltage, filament current, load resistance. This is a resistor, 5,000 ohm resistor that is in series with the plate current. This is plate voltage. The most important one going here is this one. This is plate current. I've checked this so thoroughly, there's no question that I can read AC current with this meter while there's a DC current flowing through it. It has no problem with that. So put this on current. You can also read AC, which is really important, but right now it's reading DC current. Okay, I have a backup meter over here, and the purpose of this guy, what am I doing here? 20 AC must be. So this is supposed to be reading the plate. I'm going to put it to 1000 DC. This is so we can get a very accurate reading on the plate voltage, which needs to be held steady during these tests at some number. And the number, some number. So this guy will also read the plate voltage. It's just not quite as precise, but 250 is basically straight up. And that's roughly where we want to operate at. So this is not saying -8 because my power supply is still in standby. So by now the tube is fully warmed up, there's no doubt about that. I have a little more going on here before we get going. But you know what? I won't go into that. Let's just get the tube operating DC-wise in a stable fashion. So what I'm looking for is -8 bias, resulting in a current of around 8 or 9 milliamps DC. And if we get all that, we're ready to go to the next couple of steps. So I have a switch here which is switching the B+ I'm supplying to one plate or the other plate. I've got a number here, 1 and 2. It's just a random number. It's not, doesn't mean much. And just in case I haven't, I've shot so much video, I'm not posting it. I'm not sure what I posted on YouTube about this. So you see the tube is sitting here. I have all this stuff hooked up over here. Underneath this chassis, there's just 8 wires running between the socket here and the socket there. They're the same. So the tube is operating here. The tube pins are available over here. I have a tube extender, this brown thing, plugged in here, simply because it has terminals, test terminals, poking out of the top of it here. And all this stuff I have hooked up here, it's all these voltmeters reading voltages off of here, including the scope. As you'll see in a little bit, the scope is connected too. So right now the switch is straight up. Neither plate is getting anything, and I don't have any DC voltage being applied anyway. So let's bring the voltage up on one of these plates. I'm going to pick one. Pick that one. This meter, this is just going to get a little confusing. This meter will only show you the voltage on one of these 2 plates. So sometimes it's going to say 0. So that's okay. We'll use it to calibrate the B+, and then we don't have to worry about it anymore. So let's bring up a little bit of C- first. So here we go. It's right around -8. That's good enough for us to start. You just don't want to do this with no bias on the grid, or you're going to get kind of like a wide open tube current flowing. So now we're going to bring up the it's a little crowded in here today. Okay, so we're going to bring up the plate voltage here. You can see what I'm doing. I'm turning this knob. I keep an eye on the voltmeters. So this guy's going to go straight up, and this guy should say 250. If everything is working right, nothing appears to be going anywhere. Okay, so there we go. So I'm not getting this meter to work. So maybe I've hooked this meter up to something. I've done something with it without realizing it. Let me just make a quick check. Okay, that's on the cathode, so the black is on the cathode. Just looking down here. The red is on this yellow clip, which is clipped to a grid. We don't want it on the grid. We want this. What's happening? This is all kind of loosey-goosey. Sorry about that. Okay, we want this on the plate. Plate is right here. There we are. There we are. 150, 160 volts. Good. I'm not exactly sure what all was going wrong there, but you know, this is how it's been the whole time I've been doing this. Lots of times where I'm really not sure what just happened. So we want this to be 250 minus 8, 0.6, and then we're watching this to make sure this doesn't go over 20. If this goes over 20 milliamps, I'm pushing the tube a little too hard. I'm going to raise the voltage now to 250. And I try to set it fairly accurately. The reason I'm picking 250 is because that's the voltage that is used for a lot of the statistics that are written in the tube manual. You see we're getting up close to 10 milliamps there. Okay, so that's 250 volts. Now we'll make this exactly minus 8. Oops. There we are. That's exactly. And there's our DC current. So what this tells me is that in a DC arrangement, everything is working here fine. I'm just going to knock this down 1 little volt if I can. It's a little hard to do. Okay. Now the next step here is to put a signal onto the grid, an alternating signal onto the grid, and see it on the plate, and then measure the AC current in the plate circuit, which is tricky, but this meter can do it. This is the savior of this whole thing, is this guy. So the reason I want the scope on is to make sure I'm not clobbering the tube, I'm not driving something so hard it's in cutoff in some way or something of that sort. Okay, so we're going to make use of the sweep generator, but we're not going to sweep anything with it. It's just going to be running at, where'd you go? Running at 300, about 300 hertz. It's kind of a low tone to your ear. Okay, running through everything again. 250 volts, minus 8 on the grid, 0.6 amps in the filament, a steady current of 9.5 milliamps. So now I'm going to start applying signal to the grid. So first I'm going to change this to an AC meter. It basically shows nothing. And you can watch the signal come up on here, but this is voltage, of course. This is output and this is input, but this is just kind of meaningless. It's all about that current meter. So we're going to bring the voltage up. Now I remember why I had that voltmeter on the grid. I just remembered. So we're going to switch it. So I've got this set to 250. That calibrates this meter for me. So I know exactly where this meter needs to be in order to have 250 volts. And the scale is, of course, slightly off on the old meter, but not by much. So I can then use this meter to read the AC voltage being applied to the grid, which is what I want to do. So first I'm going to disconnect the lead. That's exactly what I was doing last time around. I just kind of forgot. Put this onto the grid. Okay. So now we're reading the AC voltage that's on the grid. Is it a coincidence? It's exactly a volt. Yes, it would be a coincidence. So this instrument, when you turn it on and off, you're also rotating the amplitude control on it. So basically, if you turn it off, the amplitude goes to 0. You're always starting from 0 amps. Anyway, not to worry about it. Let's prove that this is doing something. So we're seeing the voltage on the grid here and we're seeing the current flowing in the plate circuit here. So I'll turn up the voltage here. We should see the current go up. Shouldn't be too complicated. Well, for some reason this isn't going up. It's kind of weird. It's stuck right on 1 volt exactly. How does that work? Okay, so something's wrong with my setup. Let's just look through it. Okay, this meter is on the green to the cathode. The other lead from the meter. The lead from the meter is the yellow clip lead. Yellow clip lead. Oh, it's something over here. This is just not working out so well. I see it. I got a clip. Yeah. Zero. Does that make sense? I don't think that makes any sense. Yeah, 0 might make sense. So we have basically 0 current, because this is in milliamps and the decimal point is there. If you have a little trouble seeing it, it's actually 0.01 milliamps there. I mean, it's minuscule. So we'll apply a little voltage to the grid, and right away you see the current come up. Excellent. We are where we need to be. So now we're going to put a 1 volt AC signal onto the grid here. And you can kind of see things happening on the scope too. Get up to 1 volt. 1 volt. 1 volt of signal. Ooh. A little high there right at the end. Okay, so we're ready now to calculate the to make the measurements needed to calculate the mutual conductance. And it has to be said this way. This is the mutual conductance when the plate is 250 volts and the grid is -8. You really have to say these things, I think. So I'm going to write down some numbers. So we've got 1 volt RMS AC on the grid. And we've got 1.5. Excellent. Nice numbers. 1.5 milliamps in the plate circuit. And I'm going to increase this by half a volt. I'm going to try and see if there's enough headroom for that. As soon as I remember where it's coming from. Half a volt. Can we get there? Oh yeah, we're there. There we are. Okay. Now we read this, 2.29. I'll write it down on my sheet here. 2.29 when you have 1.5 volt signal. Okay, here we go with the math. You ready for this? How many times have I done this calculation in the shop over the last few days? So GM equals the change in plate current. The change is the subtraction of these two numbers. Subtract away. 9. 2, 12, 7. So 0.79. So I'm bold enough to show you my arithmetic. I may get this wrong. Does that seem right? 0.5, 2.25. 0.75, yes, seems exactly right. So that's the delta in the current. And the delta in the voltage is 0.5. So we take the deltas, 0.79 divided by 0.5 times 1,000. I'm going to use my calculator on this. 0.79, this is the exciting moment, divided by, I don't think it looks right, 0.5 equals that times 1,000 times 1,000. Can you see the number there? 2,000. 2,000. Really, I'm going to repeat this because it's just too amazing. Isn't it amazing? It's amazing. Let's repeat it. 0.79. Like I'm almost shaking here because of the number of times I've done this and come out with a berserk answer. Usually because something of all these variables in here. Something's not quite right. I think I got it. Yeah. Oh, wait a minute, this came out different. One more time. Stop talking while you do it. You guys are busily calculating it yourselves. You should. Okay, I'm going to get a different number. Okay, so I don't know where the 2000 came from, because there's no way you can do this and get 2000. What I actually got, 1580. And now I'm going to show you something here. 1580, eh? 1580. 15. 14. Lots of readings. So let's think about this now. So you know what? I never wrote down the GM from the precise, but I think it was around 1500. So I got two tube testers telling me it's 2000. One of them telling me it should be 2000, and I got my setup telling me it's 1500, and this guy telling me it's 1500. But here's the thing that has come so clear to me about doing all this, that even if we look in the book, you say, well, what is the GM for this tube? So here it is here, trans conductance. Why, it's 3000 under this condition and it's 2600 under that condition. I should have got 2600 out of this, actually, according to that book. There we are. So, I don't know what to think. I really don't know what to think. Oh my gosh, what a kind of a crazy situation this is. Well, what I am going to do is I'm going to spend the rest of the day thinking about this some more, and I'll probably, just like yesterday, I'll be in here over and over again trying little things here to try to bring all this stuff together so all these instruments say the same thing. In a sense, they do say the same thing. They say the tube is good. They all say that. All these tests have shown that. But what they don't agree on is the exact measurement of the mutual conductance. And now I realize it's really dependent on how you operate the tube. So, conceivably, each of these commercial tube testers has, conceivably, almost certainly, has been designed with all this in mind, and they figured their way around everything with these tube testers. So, is there any one of these I think is better than the other? Well, I'll tell you after I finish my bag of tubes. And I misplaced my bag of tubes just now. But that's what I'm going to do also the rest of today. I'm going to run all these through some, if not all, these tube testers. So we'll see. We'll see what happens. Thanks so much for watching. This has been a far more complicated thing trying to set up this stuff here than I ever expected. And it is what it is. So see you in the next video.